about this work on percolation and NP-Hardness. And then I'll tell you about this follow-up work on coloring random subgraphs of a fixed graph. And so for me, the second part is kind of more interesting than the first part because there are questions there that I would like to know their answers. But anyway, I'll start with percolation and NP-Hardness. So I will tell you what's percolation. So basically, percolation is the name of this process in probability theory where we start with a graph, we remove some edges at random, and we see what we get. What's the new graph that we're getting? So I suppose the most standard model is this GNP model. And let me present it. Maybe the way is a bit non-standard. So we start with a complete graph Kn, just click on n vertices, and we remove edges. We remove each edge with probability 1 minus p independently. Okay, so that's a standard model. And for this model, so basically we keep each edge with probability p. So this is a super standard model and we know everything about this. And for example, when p is 1/2, we know what's the maximal clique or independence set or chromatic number. And I'm sure some of you know the exact constants and the constants in the second term and the third term and the concentrations and everything. Okay, so we'll not talk about this. I'm just saying that this is a standard model. We can also ask about algorithmic problems, right? So okay, so we know that the maximal clique in this model is with high probability 2 log n. But can we find the maximal clique in polynomial time, let's say with high probability, right? So there is a small chance that the graph that we'll get will be very hard, but somehow on a typical graph, can we find the maximal clique? Or we know what's the optimal coloring. So it's like n divided by log n and there is a constant there. Can we find an optimal coloring? So these problems on random graphs are sort of easier than the worst case in the sense that we have some approximation algorithms for these problems, but still we don't have optimal algorithms for these. So for example, for max clique, we know that the GN1/2 has a clique of size 2 log n, but we don't know an algorithm that finds a clique that's significantly more than log n. I think so. All right. So having said that, here is the problem that I would like to talk about today. So let's not talk about a random subgraph about GNP, but rather let's fix an arbitrary graph. So maybe this graph is, an NP-hard instance, whatever this means, right? So it's kind of a worst case graph. And we'll choose a parameter P. And then I'm going to take edge percolation of this graph. Namely, I'm going to remove edges from this graph G, and I will denote by GP the subgraph obtained from G where edges are removed independently and I keep each edge with probability P. Okay, so GNP is a special case of this where G is a complete graph, but maybe for some graphs, this problem is like more complicated computationally. Okay, so what's the problem? So for example, right, so that will be, it took me like 5 hours to draw these pictures. So, okay, so only one of them. One of them I took from the internet and the other one, just removing the edges, it took me hours, really. So this will be our, picture that we keep that we think about, right? So we start with the graph and we remove some of the edges. And I would like to ask about the algorithmic problems on these graphs. And for the rest of the talk, P will be 1/2, okay? So I will not talk about other Ps. So specifically, I will focus on the chromatic number of a graph. So I will state it explicitly. So a chromatic number, the problem is, so yeah, I'm sure you all know this. Okay, so we're given a graph and we want to assign colors to the vertices. So we want to assign a small number of colors because we have only like 3 or 4 markers of different colors. But for each edge, we want the endpoints to have different colors. Right, so for example, we have edges where one endpoint is red and the other one is blue or something. So we don't have an edge with endpoints having the same color. That's the chromatic number. Here's a theorem. In general, this problem is NP-hard. What does it mean? It means that there are graphs that we don't, right, that for every algorithm, there are graphs that for every polynomial time algorithm, there are graphs on which we don't solve they don't compute the chromatic number correctly on these graphs. Okay, so there are many such graphs, but basically sort of these NP-hard graphs, it's not clear how natural they are or where they come from, right? Maybe these are some very adversarial graphs. So we would like to kind of stretch it a bit to more, I don't know, general graphs or something, right? To say that, you know, it's not one specific hard graph or something like that. It's more. Right, so for NP-hardness, so for the worst case, even distinguishing between 3 colorable graphs or requiring more than 3 colors, it's NP-hard. But what about, let's say we're not given just the graph G, but we take G sub P. Does this problem become easier? So what do I mean by G sub P? Let's say I'm giving you a graph, but I'm not asking you to compute the chromatic number on this graph. But instead, we remove half of the edges with, you know, each edge with probability 1/2, and I'm asking you to solve the problem on this subgraph. So there's no crypto or no tricks, really. We look at the sky, we see the randomness, we remove together the edges. Okay, so no tricks. I suppose if there were crypto people here, they would, you know, they would come up with all sorts of interesting ideas about this, but we both know the randomness, okay, or all of us know the randomness. So the randomness is shared and no tricks there. So the question, does this problem become easier? Okay. And here is a theorem that even if we remove half of the edges at random, the problem stays hard, stays NP-hard. It's a bit not clear what I mean by NP-hardness because, right, we need to define this decision problems and it's with high probability. So what do I mean? I mean that if with high probability, let's say over both the randomness of the removed edges and let's say the randomness of the algorithm, if with high probability we can compute the chromatic number of the random subgraph, then we can also compute the chromatic number of the original graph. That's the statement of the theorem. Is it clear just what's the statement of the theorem? It's not a hard thing to prove. I'm just kind of illustrating you know, one example. Okay, so if we can solve the problem with high probability on random subgraphs, then we can also solve it on the original graph.
But you mean on random subgraphs of possibly some other graph, right?
Yeah. So the input is worst case G, just in the like in the NP case, right? So the G is still worst case. It comes from this, you know, from this adversarial guy or whoever gives you a hard instance.
So basically, it looks that if you take a big blow up of any graph,
right? Yes.
Yeah. So it's.
Yeah, exactly.
Okay. Mm-hmm.
Yeah, that's the proof. Again, I'm not saying it's a hard proof. Just to illustrate the idea, right? So what are we really doing? So okay, so that's the theorem. If we could compute the chromatic number of a random subgraph, we could compute it also on the original graph. So what do? Yeah, to prove NP-hardness, we show a reduction. So given a graph G, we compute a graph G prime that has 2 properties. So first of all, the chromatic number of G or G prime is the same. And also with high probability, it should be, will I be able to do it on the fly? Let's see. The chromatic number of the random subgraph has also the same, is also the same. And yeah, the proof is basically you take a graph blow up. Okay, so you start with a graph G and you want to somehow make the edges thicker in the sense that on one hand, yeah, I'm going to remove half of the edges, but they will kind of still should be visible. Okay. And yeah, so the reduction, I don't remember. We worked with this like a long time ago, like 3 or 4 years ago. So I don't remember. I think the reduction, we knew immediately that it should work. Just the question how to prove it. Maybe a first attempt would be to say that the G1/2 still contains a copy of the original graph. But I don't believe this quite works, right? I mean, so what's the blow up? Let's say we blow up each vertex into n vertices. So in expectation, the number of copies is large, but somehow there are too many correlations, so things will not work out exactly right. Still, we managed to make it work. We say that, look, in every cloud of, so each vertex is blown into a cloud. So between every 2 clouds, there are many edges after this percolation step. So somehow, given these many edges, we show a sort of a decoding algorithm. So you give me what's the coloring of a cloud, I choose the majority, and then I give it as a color to the original graph. Something like that. If you followed it, great. If not, that's not the focus, okay? So okay, again, I will say the naive idea of just trying to look for the original graph in the percolation of the blowup, I don't think that works. Still, there's another way that does work. How? Just look at the majority of colors in each cloud. Okay, I will not do the full proof here. All right, so that's the first example. What about other NP-hard problems? So we show a bunch of problems on which stay NP-hard. So for example, like 3-SAT, we defined a notion of, I don't know, we remove random edges, random clauses, or random variables, or something like that. We show that all these problems stay NP-hard. But in general, some problems can become easier. One such example is the clique problem. Okay. So if we're given a graph G, so previous example was showing that some problems stay hard. This example shows this problem becomes easier. I'm not saying it's in P, but I'm saying it's easier. So here is the problem. The problem is the max clique problem. So given a graph G, if we want to find the maximal clique in a percolation of G, then we can find it, well, maybe not in polynomial time, but in quasi-polynomial time, in n to the log n. And the reason, yeah, it's again sort of trivial, but it's more kind of, illustrates the point, right? The reason is, even if we started with a complete graph, the subgraph would not have a clique of size more than 2 log n. So that's certainly true for any G, right? If it's true for the complete graph, it's certainly true for any other graph. So we can just do brute force and find it. So max clique is hard on worst case instances, but on these semi-random instances, this problem becomes much easier. All right. So I think that's the first part. That's about percolation and NP-hardness. Questions so far? Right. Yeah. So maybe this example, right? Maybe for this specific clique problem, maybe it's natural to ask: are there any families of graphs on which we can actually find polynomial time algorithm, while originally they were NP-hard? Possibly. I don't know. I haven't thought about it too much. Just when preparing for the talk, I thought it would be a nice problem. Okay, so are there families of graphs on which max clique is NP-hard, but when we remove half of the edges at random, the problem becomes polynomial time? So right, so we kind of think polynomial time as a standard for efficient algorithms, and we don't like this log n in the exponent. All right, so if there's no questions so far, so we're, okay, so 15 minutes. All right, so I will tell you about the second part. And the second part is this question of Boris Bukh. And so the story is, we wrote that paper on percolation and NP-hardness, we submitted it to ICALP, we were wondering about the chromatic number of random subgraphs of this, of a given graph G. And we kind of mentioned this problem in open problems or something. I will tell you exactly what's the problem. And one of the reviewers said, yeah, but this is a well-known open problem. And we said, oh, that's very nice. So I will tell you a well-known open problem, okay? Here is the problem. So again, fix a graph G. And let's say we know the chromatic number of G. And think of chromatic number of G as some number K, okay? So it's not, and think of K as small. Okay, so think of K as maybe like 20 or log n. So much smaller than n. What can we say about the distribution of chi-GP, of the chromatic number of the subgraph compared to the original chromatic number? Okay, and as a first approximation, what can we say about the expectation of chi-GP as a function of the original chromatic number? Okay, so let me give you a couple of examples. Yeah, I enjoyed doing this picture so much that I put it on every slide. So first of all, it's clear that the chromatic number only goes down, or it can never go up. Also, so let's say K is the chromatic number of a graph. If G is a union of many K cliques, if we want it to be connected, maybe we connect it by a path or something. How many, maybe like exponentially many or exponentially K squared or something, then the chromatic number stays very close to 1, right? Because if we remove half of the edges at random, then maybe one of the cliques, and there are many cliques, then one of the cliques will just survive with some probability. Okay, so if the number of cliques is, yeah, I guess exponential in K squared or something, then the probability of that the chromatic number stays the same K as it was before will be very close to 1. On the other hand, if G is just a complete graph, so I use the letter N, but maybe it would be better to use the letter K for the number of vertices in, so if we start with a clique on K vertices, then the chromatic number becomes K divided by log K. Okay, so we have kind of two examples. In one example, if it's a union of many cliques, the chromatic number stays close to K. If G is just one clique, then the chromatic number is K divided by log K. The question is it true that for every graph G with chromatic number K, in expectation, the chromatic number is never below K divided by log K? So basically we can compare it to just starting with a clique on K vertices, maybe up to constants. Is the question clear? Okay. So we have, right, do we have examples where the chromatic, or maybe to say that this is wrong, would be to show an example of a graph with chromatic number K, such that when we take G1/2, the chromatic number drops by more than a log n, than log K factor. Okay. So here is what Boris proved. So one thing he showed is that the chromatic number, the expectation is at least K divided by log n. And so, yeah, so he has this, one of his pages on his homepage is like open problems I like or something. And it's there. So in particular, if K is polynomial in N, this is comparable to K divided by log K, which sort of answers the question. Okay, that's nice. But I would like to think of K as being really small, right? Maybe 100 or log N or something like that. All right, so in this paper with Huck and Daniel, we showed that for if a graph is kind of well-behaved, in one sense well-behaved, if the independent set of a graph is, well, inverse of the chromatic number, maybe up to constants, then we get a positive answer to this question. So well-behaved means if you take G and P or G and D with the right parameters, then the chromatic number will be maybe close to K, and also the chromatic number and the independent set, they behave, well, the chromatic number times the independent set is approximately N. Okay. Another work related to this is this work of Mohar and Wu. And they said that they basically give a positive answer to this question, but not for chromatic number, but for fractional chromatic number. So what's fractional chromatic number? It's sort of the linear programming analog of chromatic number or something. Okay, so if you know this, yeah, then my definition, you already know it. And if you don't, basically kind of the natural LP you will write will kind of give you probably the fractional chromatic number. Anyway, so these are I think the known results, at least those I'm aware of. Okay. So if yeah, that's a super nice open problem. Prove that the expected chromatic number is at least K divided by log K for all graphs, or disprove it. Okay, so here I gave you one open problem. Everything else, I will tell you a little bit I know about this problem. But the important thing, I told you a nice open problem. All right. So the next 10 minutes I will, or less than 10 minutes, I will show you some proofs. Okay. So let's start with an easy proof. First of all, an expectation is at least square root K. Okay, so square root K is again easy. In fact, it's square root K with probability at least 1/2. Why is that? So observe it, if we take H to be a random subgraph of G and we look at the complement of G, then they have the same distribution. Well, just I put each edge either here or here, and they have this right with probability 1/2, so they have the same distribution. On the other hand, H and the complement of H together cover all the edges. So it means that if I take the best coloring for H and the best coloring for the complement of H, and I take their product, right? So I take all a coloring that satisfies all edges in H, and I take all coloring that satisfies all edges in the complement, then the product, this pair, will satisfy all edges of G. So it means that the product is at least the chromatic number of G, which implies that in expectation, right, that one of the two must be at least square root K. Not a hard proof, but I mean, it's a start. Okay, so now I'm getting to more refined questions, and then I'm actually going to tell you something. We can ask more refined questions. So for example, let's, instead of looking at expectation, let's look at what's the probability that the chromatic number is, let's compare the chromatic number of G1/2 compared to the random subgraph of the complete graph. Is it true that we always have inequality in the direction that we want? Okay. Is it true that complete graph is always, the probability that it's small is always larger than the previous one? Okay, so we want to show that, what do we want to show? We want to show that in expectation, the chromatic number of G1/2 is always more than what happens for the complete graph. So maybe we want to show it for every D separately. And here is a very special case. Let's start with a graph that has chromatic number K and ask what's the probability it becomes bipartite. Okay, let's ask only this simple question. What's the probability, right? What's the worst, right? What's what can be the probability it becomes bipartite? So we start with a graph that has chromatic number 100. What's the probability it becomes bipartite? let's try to compare it to the clique. For clique, the probability it becomes bipartite is exponentially small in k squared. Why is that? So what does it mean it becomes bipartite? We have some bipartition, so that there's no edges here and no edges here. We can fix one bipartition. One of the two halves have more than k over 2 edges. Let's say this one. Sorry, has at least k over 2 vertices. It means it has at least k squared edges inside, k squared divided by 4. So the probability to kill all of them is exponentially small in k squared. The only thing left is to do union bound over all partitions, but the number of partitions is only 2 to the k, so the exponentially small in minus k squared wins the union bound. Okay, so that's easy. If we do it for an arbitrary graph where k is small, then this argument doesn't work simply because the union bound is potentially much larger than this probability, right? Because the union bound depends on n, while the probability depends only on k. Still, here is a theorem that I actually can prove. Okay, so next, I have 2 minutes to prove a theorem. All right. Let's start with a graph with chromatic number k, and we ask what's the probability it becomes bipartite. So the probability it becomes bipartite is exponentially small in k squared. Okay, so that's comparable to the clique case. And let me tell you in 3 lines what's going on. So the key lemma is the following. So suppose that every 8 coloring of a G leaves many monochromatic edges. Okay. If this happens, then the graph becomes bipartite with only tiny probability. So that's the key lemma. So again, the key lemma says that not only the graph is not 8 colorable, but stronger than that. It leaves many monochromatic edges. Okay, when I try to color it with 8 colors, it leaves many monochromatic edges. If that's the case, then the probability it becomes bipartite is exponentially small in T. How do you use this lemma? Let's see. So let's take k, and let's say k is some multiple of 8. So think of k as like large, like 100 or something. If I try to color it with only 8 colors, one of the colors will have, so one of the color classes will have a chromatic number that's at least k divided by 8. Okay, so I partition it into 8 parts. The chromatic number was k. I partitioned it into k parts. One of the parts had at least k over 8. K over 8. The chromatic number stays at least k over 8. Here's a small fact. If the chromatic number is at least k over 8, it must have at least order of k squared edges inside. So we apply the lemma. And by the lemma, it says that only this part, the probability that this part will become bipartite, is exponentially small in k squared. And there is a constant c from the lemma, and there is another constant from the omega, but basically that's the proof. So I think I'm running, I'm sort of out of time, but that's the proof. I don't know. I kind of did it in 2 minutes. I'm not sure it was clear. But basically the conclusion is that, do I have the conclusion here? Yeah. So the conclusion is that if we want to ask what's the probability that G1/2 is bipartite, then we can compare this probability to what happens in the case when we start with a complete graph on k vertices. And I would like to prove it for larger k's. So maybe I can prove it for k equals 3 or 4, but at some point this technique doesn't work anymore. All right. So maybe I'll conclude with some open problems. So one open problem, I told you this one. prove that for every graph with chromatic number k, when we remove half of the edges, the chromatic number in expectation or with high probability stays at least k divided by log k. Maybe as an intermediate step, try to do some comparison, right? What happens on an arbitrary graph with chromatic number k as opposed to the complete graph. And maybe there are some intermediate, some related problems. So what happens when we keep edges with probability p as opposed to probability p over 2 and so on? So what's the relation between all these expectations? I'm not sure. So these are some of the open problems that I have. I think I'll stop here. Thank you.